Hi, this is John Whitaker again for the Mathematical Analysis 2 class, and this is going to be our 11th lecture. And what we want to talk about is a continuation of Riemann-Stieltjes integral functions and some facts about them. Let's start off with a new fact for this lecture. So here's the theorem. It says if f is monotonic on A to B, and if alpha is continuous on A to B, then f is a Riemann-Stieltjes integrable function with respect to alpha. Okay. And let me say that alpha is still assumed to be increasing. Okay, let's look at its proof. We let epsilon be greater than 0 be given. And we have a mechanism by which we can prove that a function is a Riemann-Stieltjes integrable, and that is that we want to show that the upper Riemann integrals, upper Riemann-Stieltjes sums minus the lower Riemann-Stieltjes sums are less than epsilon for some partition. And so here's what we're going to do. We're going to say for any positive integer n, choose a partition such that the delta sub alpha i's are equal to alpha acting on B minus alpha acting on A all over N. This can be done by the following process. So first of all, we note that alpha of A is less than alpha of A plus alpha B minus alpha of A all over N. This is because alpha is an increasing function and B is bigger than A, and so we have this inequality. But this is going to be less than alpha of B. So what we think of as this quantity is really the distance between alpha of B and alpha of A divided by N. Okay? So to get from alpha of A to B, you really have to add up this distance N times to alpha of A. It's definitely less than alpha of B. Okay. Since alpha is continuous on A to B, there exists an x sub 1 with x sub 1 being in between A and B, such that alpha of x sub 1 is equal to alpha of A plus alpha of B minus alpha of A all over n. And this is true by the intermediate value theorem. Okay. Now note, we're going to continue this, extend this process. Alpha x sub 1 is going to be less than alpha of A plus 2 times alpha of B minus alpha of A over n, which is less than alpha of B. Since alpha is continuous, okay, there exists an x sub 2 with x sub 1 being less than x sub 2 being less than b, such that alpha of x sub 2 is equal to alpha of A plus 2 times the quantity alpha of B minus alpha of A all over n. And that's again by the intermediate value theorem. We continue this process. Well, I'll leave this, we continue this process. Until we note the existence of alpha x sub n minus 2 is less than alpha of A plus its n minus 1 times alpha of B minus alpha of A all over n. And we say since alpha is continuous, there exists x of n minus 1 such that x of n minus 2 is less than x of n minus 1, which is less than here b, and alpha of x of n minus 1 is equal to alpha of A plus n minus 1 times alpha of B minus alpha of A. I'm going to write this on the next line. Alpha of x sub n minus 1 is equal to alpha of A plus n minus 1 times the quantity alpha of B minus alpha of A all over n. I believe I made a mistake earlier that I want to correct. So let's go back to what I've written here at the bottom with this alpha of x of n minus 2. I think that that should say there should be n minus 2 here. Okay? That's a mistake. That matches here with x of 2 being 2 times this guy. Okay? Okay. Wait a minute, this should have been n minus 1. I'm sorry. It's going to be less than this part. Yes, it's going to be less than this part. Okay. And so, yeah, that was correct what I had written. I'm sorry. Got confused for a second. That's correct. Okay. So we're doing the next to last one here. Sorry. And it's equal to this quantity. That's correct. Okay. Yeah, that's correct. Okay. Then, to form our partition, we use that alpha, we use x of naught is equal to A and x of n is equal to B to form the partition. Okay. So that's how we create the partition that we were looking for. That is one whose the delta of alpha sub i's are equal to alpha of beta minus alpha of A over n. So we have that partition. Now we look at cases. So the first case, remember we're assuming that alpha is monotone. And so the two cases, we're assuming, that F is monotonic. And so the two cases are if F is monotonically increasing on A to B, then what we have from our previous definitions is that the m sub I will be equal to alpha of x sub I for our partition, and the little m sub I, nymphema, is going to be equal to alpha evaluated x sub I minus 1. And now, if we look at the upper Riemann still just sum with respect to this partition of F and alpha minus the lower Riemann still just sum with this partition F and alpha, we get that that's equal to, it's the sum, it's really alpha B minus alpha of A all over n times the sum, as I runs from 1 to n, of big M sub I minus the little m sub I. And that's equal to alpha B minus alpha of A over n. And then this would be the sum as I runs from 1 to n. This is F of x sub I minus x sub I minus 1. Now, a lot of those terms in the sum will cancel out, and what we just end up getting is alpha of b minus alpha of a divided by n. That's our delta alpha sub I for each one. And then times the sum, oh, well, I said most of them will cancel out. What we're left here is just f of b minus f of a. And this is going to be less than epsilon. This is going to be less than epsilon, not all the time, but for certain choices of n. So it's going to be less than epsilon. When n is taken to be bigger than alpha beta minus alpha of a times f of b minus f of a all over epsilon. That's great. And so in this case, f is Riemann-Stieltjes interval with respect to alpha. We also have another case, only other case, case 2, and that is if f is monotonically decreasing. Okay. And then the little m sub I would be f of x sub I and the big M sub I will be equal to f of x sub I minus 1. That's correct. So when you put in the smaller value, it yielded the bigger output value. And now when you look at the difference between the upper and lower Riemann-Stieltjes sums, that again is going to be equal to alpha of A minus alpha of B over n times the sum. Here it would be the big M minus the little m, and so this is as I runs from 1 to n. That's just going to be f of x sub I minus 1 minus f of x sub I and that's going to be equal to alpha of B minus alpha of A. I had miswritten that before. Let me make that change. Sorry. Here at the bottom, this should be alpha of B minus alpha of A. That's what it should have been. Okay, so note that change, that correction. Okay, so we have alpha of B minus alpha of A over N, and then this, the sum that we had previously, there's a lot of cancellations going to happen, but this is going to be alpha of A minus alpha of B. And that's going to be less than epsilon when N is bigger than so it will be alpha B minus alpha A times f of A minus f of B over epsilon. Okay? Thus, we have f is an element of the Riemann-Stieltjes integral functions with respect to alpha in this case, or in all cases. And that concludes the proof. We next want to look at a theorem that I think is somewhat difficult to, if you will, to write up, but it's also listed in our text. The text is much more concise in its proof, but I think I'm trying to add some details here for clarity. But here's what the theorem says. It says, suppose f is bounded on A to B. F has only finitely many points of discontinuity. And alpha is continuous at every point at which f is discontinuous. Then f is a Riemann-Stieltjes integral function on alpha. Okay. So we're going to prove this by using the theorem we've been using several times, by showing that there exists a partition such that the upper sum minus the lower sum of those partitions is less than any given epsilon provided. So we start off by the proof by let epsilon be greater than 0 be given. Okay. And we designate M to be equal to the suit of all the output values inside absolute value of F. And so this is over all x's in A to B. And let E be the set of points of discontinuity. I'll say down here, of f of x. Okay. Okay. Since f is finite, we can label the elements of E as, let's say, t sub 1, t sub 2, all the way up to t sub k. We'll label them in order. T sub 1 is less than t sub 2, is less than, all the way less than t sub k. Since alpha is continuous, at t sub I for each I, then there exists a delta sub I such that for all y element of A to B with the absolute value of y minus t sub I being less than delta, then the absolute value of alpha sub y minus alpha sub ti will be less than epsilon. And so this delta was delta sub I there. Okay, and it's true it's less than epsilon, but what I really want it to be less than is epsilon over 4 times m. So that the inequality that we want will come to pass. Okay. Okay. So, for all y element of A to B with absolute value of y minus ti being less than delta sub I, then I should say delta sub I divided by 2. Then the absolute value of alpha of y minus alpha sub ti will be less than epsilon over 4m. So I'm just getting a smaller delta sub I as my bound. So we consider the following cases. So, first case is that t sub 1 is equal to alpha. So is equal to A, the first point of discontinuity for F. And t sub k is not B. So the last point of discontinuity isn't the end point of the interval. And so we choose delta sub I small enough such that the following intervals and so what are our following following interval. It's a up to a plus delta sub 1 over 2. Then here we have t sub 2 minus delta sub 2 over 2, t sub 2 plus delta sub 2 over 2, and intervals of that form, all the way up to the last one being t sub k minus delta sub k over 2, up to t sub k plus delta sub k over 2. Are in A to B and are all disjoint. Case 2 is t sub 1 is different from A, and t sub k is equal to B. So it's the right-hand endpoint that's the point of discontinuity for our interval, not the left. And so again, we choose delta sub I is small enough such that the following intervals the first interval we'll look at is t sub 1 minus delta sub 1 over 2 up to t sub 1 plus delta sub 1 over 2. You know, this interval obviously contains a t sub 1. It's the interval, it's the neighborhood of t sub 1 with radius delta sub 1 over 2. And then we keep going all the way up to, let's say, t sub k minus 1 minus delta sub k minus 1 over 2 up to t sub k minus 1 plus delta sub k minus 1 over 2. And the last one we have, I'll write it down here, is going to be up to b, and here it's going to be b minus delta sub k over 2 are in A to B and are all disjoint. So no overlap. Okay. Case 3. So this case we'll have t sub 1 is equal to A and t sub k equals to B. Then we choose delta sub I small enough such that A up to, let's close interval there, up to A plus delta sub 1 over 2. Then I'll say t sub 1 minus delta, so this is t sub 2, minus delta sub 2 over 2 up to t sub 2 plus delta sub 2 over 2. All the way up to this t sub k minus 1 minus delta sub k minus 1 over 2 up to t sub k minus 1 plus delta sub k minus 1 over 2. And then we have this last interval, which is, of course, b minus delta sub k over 2 up to b. n a to b and are disjoint. Okay. And in the last case, we have t sub 1 is different from a, and t sub k, the last point of discontinuity, is different from b. And we choose the delta sub i's small enough such that here we have t sub 1 minus delta sub 1 over 2 up to t sub 1 plus delta sub 1 over 2, all the way up to this last interval of t sub k minus delta sub k over 2 up to t sub k plus delta sub k over 2 are all n a to b and are all disjoint. Okay, so what we're going to do is, if we rename intervals, the intervals, in each of the cases, as u sub j up to b sub j, and note that we have alpha of b sub j minus alpha sub u sub j. So if we look at that, that's going to be less than, I think it's epsilon over 4n, and that's due to the continuity. Now, by removing the intervals of the form u sub j comma b sub j, these are open intervals, or, we have certain cases where we have a plus delta sub 1 over 2, or we could have the form b minus delta sub k over 2 to b, or the last case was we had the form both types for case 3. This was for case 1, this was for case 2, and this is for case 3. So we take all those forms, depending on what cases we are, out from A to B to form a set K. Then K will be compact. And all the discontinuities of F will be removed from K. So F is continuous on K and thus, since K is compact, F is uniformly continuous. On K. Okay. And so, here's what we have. So, there exists this delta such that the absolute value of f of s minus f of t will be less than epsilon over 2 times alpha of b minus alpha of a. And that's for all S, T element of K. With T minus S being less than delta. Continuity statement. Now, we form a partition. Form B partition, P by x sub naught equals to A, x sub n equals to B, the last one. Include all u sub j's and v sub j's. Okay? In addition, this is all we add to it. In addition, okay, add in enough I'll say y sub i's that do not belong to the interval from u sub j to v sub j. So they're outside of those guys. Such that the y sub i's added, okay, form a partition with the x sub I minus x sub I minus 1 is less than delta, and that's for all x sub i's minus 1 different than u sub j's. Different than a u sub j. think this thing is kind of tough to follow this proof. And so let me give the idea graphically of what we're aiming for. So the idea is that we're splitting up moving this partition from A to B. And what we have is some regions like U sub J up to U sub B. Okay, in here, we control the partitions by alpha being continuous. We control the difference in, not the partition, we control the difference between the upper sum and the lower sums by alpha being continuous. And here, in between things, maybe we have a U sub I minus 1 up to a U sub I, U sub I. And we control this region. So we're splitting up A to B into these types of regions. So one of them's based on alpha, and then other regions are formed by throwing in some more Y's into our partition. And this one we control by F being continuous. Okay, that's what we have. Okay, so here's one thing to note before we look at the difference between the upper and lower sums, is that the maximum value, or the suit, minus the m on an interval, is going to be less than 2 times m. Remember, m was the absolute value of the f(x), the suit of that. And so, the upper sum minus the lower sum, okay, that's going to be equal to the sum as I runs from 1 to n of big M sub I minus the little m sub I times the delta alpha sub I. And now we're going to break this sum into 2 parts. We're going to do this as a sum where over the i's, where x sub I minus 1 up to x sub I, okay, contains points of discontinuity. I mean for F. And that's still the same quantity, m sub I minus the little m sub I, delta alpha sub I, plus the sum over the i's, where the x sub I minus 1 up to x sub I of our partition does not contain points of discontinuity. And that's again of the m sub I minus the little m sub I times the delta alpha sub I. Then that's going to be less than or equal to 2m. And then for the points, for the sum that contains points of discontinuity, that's going to be less than epsilon over 4m plus the sum i's no discontinuities. And here I'm going to say epsilon over 2 times alpha of B minus alpha of A times the delta alpha sub i's. And that's going to be less than or equal to Well, of course, the m's cancel, the 2, it's epsilon over 2 plus, here, this is going to be epsilon over 2 times alpha b minus alpha of a, okay, times the sum over these i's, no discontinuity. I should say in x sub I minus 1 up to x sub I of the delta alpha sub I. Now look, if you were to add up all the alpha sub i's over the whole partition, you get alpha b minus alpha b. So this is definitely going to be less than epsilon over 2 plus epsilon over 2 times alpha of b minus alpha of a times alpha of b minus alpha of a, which equals to epsilon. So this says that f is an element of the Riemann-Stieltjes integral functions with respect to alpha. Okay. Let me say there's a little bit of problems that could happen in the proof that I presented. First of all, m was equal to the suit of the absolute values of the f of x. Now, I'm dividing by m here, so there's a possibility that m could be 0. If m were 0, that would mean that f of x was a constant function. Okay? And so we couldn't have these points of discontinuity, so that really can't happen. But then there's a chance for the alpha sub i's, that maybe with them being monotonically increasing, we have the case that that could just be a constant. Okay? That could be the case. And so this change would always be 0. And so our Riemann-Stieltjes integral would just be 0 in that case. Okay? And so this guy would be 0. And so we would handle that as a separate case, but we would just get 0, so f would be Riemann-Stieltjes integral. Okay? Okay, so that's what we have. Okay, ladies and gentlemen, that's enough for today, and we will begin lecture 12 next time. Thank you very much.